Question 15. A diffraction grating with G grooves per centimeter is illuminated with monochromatic light. The grating produces several interference maxima. For the mth order bright fringe, the condition for constructive interference is given by the relation m divided by g equals lambda sine theta. A student records data for different wavelengths and plots sine theta on the vertical axis against lambda on the horizontal axis. The resulting graph is a straight line through the origin. Which expression corresponds to the gradient of the graph? This question tests our understanding of diffraction gratings. Let's recall what we know. For a diffraction grating, constructive interference occurs when the path difference between light from adjacent slits equals a whole number of wavelengths. This condition is expressed in the diffraction grating equation. We also know that the slit spacing of a diffraction grating is related to the line density. Specifically, the spacing between adjacent slits is the reciprocal of the number of grooves per unit length. Now let's work through the solution step by step. We begin with the standard diffraction grating equation for constructive interference. d sine theta equals m lambda, where d is the spacing between the slits, m is the order of the maximum, lambda is the wavelength, and theta is the diffraction angle. Since the graph being plotted has sine theta on the vertical axis and lambda on the horizontal axis, we rearrange this equation to make sine theta the subject. Sine theta equals m lambda divided by d. Next, we relate the slit spacing d to the grating line density g. The grating is described as having g grooves per centimeter. To convert this into lines per meter, we multiply by 100, since there are 100 centimeters in a meter. So the line density in lines per meter is 100 g. The slit spacing d is the reciprocal of the line density. Therefore, d equals 1 divided by 100 g. Now we substitute this expression for d back into the equation for sine theta. Sine theta equals m lambda divided by 1 over 100 g, which is the same as sine theta equals m lambda multiplied by 100 g. Rewriting slightly, we have sine theta equals 100 gm multiplied by lambda. Comparing this with the equation of a straight line, y equals gradient multiplied by x, we see that sine theta corresponds to y and lambda corresponds to x. Therefore, the gradient of the graph is simply the constant multiplying lambda. Hence, the gradient of the graph is 100 gm. This is our final answer. What did we do? We started from the diffraction grating equation, d sine theta equals m lambda. Then we rearranged it to make sine theta the subject because it is plotted on the vertical axis. Next, we expressed the slit spacing d in terms of the grating line density g. Since g was given in grooves per centimeter, we converted it into lines per meter and obtained d equals 1 divided by 100 g. Finally, we substituted this expression into the equation and compared it with the straight line form to identify the gradient. Common mistakes to watch out for include forgetting to convert g from grooves per centimeter to lines per meter, or substituting g directly into the diffraction equation as if it were the slit spacing. To summarize the key ideas, for a fixed diffraction order m, the equation d sine theta equals m lambda shows that sine theta is proportional to wavelength, which is why the graph of sine theta against lambda is a straight line through the origin. The gradient of this graph equals sine theta divided by lambda, which simplifies to m divided by d. Finally, the slit spacing d is the reciprocal of the grating line density, after converting the given line density to lines per meter if necessary.